Okay, we're talking about a mass on a spring and simple harmonic motion, and let's just review real quick what all of these things mean. So we're talking about a spring with spring constant K and a mass hanging from that spring. And let's just remember that the spring constant K has to do with how strong the spring is, how stiff the spring is, right? So a bigger spring constant K means it's harder to stretch the spring, and a smaller spring constant K means it's easier to stretch a spring. And we know that Hooke's law says F spring equals minus Kx, where x is the distance that we might pull a mass from equilibrium. What we found is that if we move the mass from equilibrium, if we give it some energy, right, we're either giving it a push so it starts oscillating up and down, or we pull it from equilibrium and we let it go so it oscillates up and down, it's going to oscillate about equilibrium with this equation, with the equation of simple harmonic motion. Coming back to, let's just make sure we understand this equation. K has to do with how stiff the spring is, right? It has to do with how much force you have to exert to stretch it a certain distance. Now be careful here. Spring force is the force that the spring pulls back on, hence the minus sign. But if I want to stretch it, if this is the positive x direction, and I want to stretch it in the positive x direction, I have to pull with a force of plus kx, right? Or more. Either plus kx or more, I have to counteract the spring force. So careful about that minus sign. The minus sign just says that the spring force pulls in the opposite direction of displacement. In general, when you're thinking springs, you probably just want to think the force is kx. Now I have to think about what direction the force is. So the bigger the k, the harder you have to pull in order to stretch it away from equilibrium. And so spring force is K, the proportionality constant. It's just a proportionality constant between the spring force and the displacement from equilibrium. What are the units? Well, if the spring force is in newtons and the displacement is in meters, then the what's K called? The spring constant is newtons per meter, right? And it is a positive constant. Again, don't get confused by this minus sign. The minus sign simply says that the spring force is in the opposite direction of displacement. K is a positive constant. A small spring constant might be, 0.01 newtons per meter. You can get as small as you want, but that might be a spring in a ballpoint pen, right? Can you hear that? Right, it's easy to squish or stretch that spring, whereas a big spring constant might be 1,000,000 newtons per meter. That might be like the equivalent of a shock absorber in a car. The spring constants can be anything, and any positive constant. Okay, that's a little bit about the mass on a spring. Oh, in addition, before we get back to the equations in black, notice that I'm drawing a spring that's vertical. Well, we actually derived this for a spring that's horizontal. What's the difference? Okay, let's look at the spring that's horizontal and just remind ourselves that if this is the positive direction and I move it away from the equilibrium, it's going to oscillate around, let's say, along the x-axis in the positive and negative directions. If I move it in the positive direction, then there's going to be a spring force pulling back in the negative direction. What's a free body diagram of that mass going to look like, right? A free body diagram, we're going to have the normal force up because it's sitting on a surface. We're going to have the gravitational force down, but it's not moving in that direction. It's moving in this direction, right? I've pulled it out plus x, I'm letting go. The spring force is pulling back in the minus x direction, okay? So, excuse me. So the net force, because it's only moving along the x-axis, the net force is simply equal to the spring force, right? The net force is equal to the spring force, and that equals ma. And so therefore, minus kx equals, well, I don't even need to worry about the vector sign, minus kx equals ma, as long as I'm choosing plus to the right. Okay, and we solved that equation to get the equation of motion here. But let's just think about the vertical. I said we would talk about the vertical spring and show that it actually doesn't matter. For the vertical spring, imagine that we're displacing the vertical spring in the plus x direction. right? In that case, if we're displacing it in the plus x direction, then the spring force pulls back. Draw a free body diagram. mg pulls down. Now, does the displacement force belong here? No, because I'm displacing it and then letting it go. Right? So there's always mg down. Fs is up or down, depending on where we are relative to equilibrium. But if I've displaced it downwards, this is a free body diagram that represents represents the mass and spring. And let's write down Newton's second law. Newton's second law says that the force is down, mg, minus the force is up, kx, minus the force is up, right? The Fs is actually the magnitude of the force, and the direction is up. I've defined down as my positive direction. So it's mg minus kx equals ma. You say, okay, so that's going to give us the equation of motion for the vertical mass on a spring. Well, I wrote something wrong. Yeah, I wrote kg instead of kx. Well, trying not to go into all the detail, let's just think about what is x. Remember that x was the distance from equilibrium. But careful, what is equilibrium? Equilibrium is the position where the mass will hang without oscillating. But what if I got rid of mg? Right? If I got rid of mg, so this I'm just going to make a hand wavy argument, which you can do quantitatively quite easily. But if I got rid of mg, x would be different, right? Because mg is changing my equilibrium position. So, question of whether x is the distance from what we call the unstretched position, which indeed x is the distance from the unstretched position for the horizontal spring, because gravity isn't there to stretch it, or is x the distance from the stretched position, the new position that's given by the fact that gravity is changing the equilibrium position of this, right? So if there was no gravity, the mass on spring would be sitting in a certain place, would be sitting in a certain place, and if there is gravity, it will comfortably sit in a different place, right? Lower down. So what gravity does is it simply changes where we measure x from. But it doesn't change anything else. It changes the equilibrium position, and it doesn't change anything else. So the equation that we've got here is where x is measured from the unstretched position. We can prove that if instead we measure x from the equilibrium position, the new equilibrium position that's given by the fact that we've applied gravity, then this equation still holds for the vertical spring. In other words, these two x's are different. Both of these equations are correct, and these two x's are different, right? mg is just a constant, and what that does is, I think, actually, you can probably see, is that the fact that mg is a constant, it just gets absorbed into the fact that we're adding a constant to x, right? We are, go up to our picture, right? We're adding a constant to x to change its equilibrium position when we add gravity. So the point that I'm trying to make is, if you understood any of that, or if you didn't, is that the equation that describes the equation of motion of the mass on a vertical spring is actually the same as the equation that describes the equation of motion of a horizontal spring. All that's different is the equilibrium position, the distance that the mass starts from the end of the spring is different. So this holds for vertical or horizontal springs. That's just the equation of motion. Okay, so let's go ahead and look at these quantities and just review that omega is angular frequency. It is not angular velocity. It's angular frequency, and it's dependent on the physical quantities m and k. So it's set for you once you choose your mass and spring. Whereas phase and amplitude are arbitrary constants. We call them arbitrary constants because they are set by when you start your stopwatch, or what you do to the mass on the spring, right? If I pull the mass on the spring away from equilibrium by a distance x max, right? I let go, that is our amplitude, because think about this equation, right? x equals a sine omega t plus phi, what's the maximum of the sine function? It's 1. So x max, the maximum x can be is a. The maximum x can be is a, so a is just the maximum distance from equilibrium. You can change that for a mass on a spring. Phase actually has to do with what is the position when t equals 0. We didn't say that before. I implied it, but I didn't say it. Phase is defined by what is your position when t equals 0. So, for example, I'm going to write in red here on the equation. If, x is, well, no, actually, let me write on a new page. Whoops, that was left over. If x is equal to 1/2 a at t equals 0, right? So if we, in other words, we start the stopwatch not when it's at a maximum displacement from equilibrium, therefore the equation of motion, x equals a sine omega t plus phi, we can go ahead and plug in 1/2 a equals a sine omega times 0 plus phi, and this is what defines phi for us, right? Because the a's cancel, and we're left with 1/2 equals sine of phi, so therefore phi is equal to whatever the inverse sine of 1/2 is. And so that defines our initial conditions. It defines our initial conditions. Phi is defined by the initial conditions. It's just the phase factor. It's called a phase factor, and it's just an arbitrary constant defined by the problem. So hopefully that gives you a little bit of an understanding of the situation. We know we now have an equation of motion, and so next we're going to analyze this equation of motion further now that we understand it, and do some example problems.